Good evening, sir. Good evening, everyone. I am Husna from EC Department, Brilliant Institute of Engineering and
Hello.
Technology.
Ma'am,
Hello.
hello, madam. Just can you give me a minute? We shall
Sure.
start in another 1 or 2. I'll just inform you.
Okay,
Once
sir.
I'll once I check my screen, then I'll inform you.
Sir, okay, sir.
Yes, ma'am. I'm ready. You can just start.
Good evening, all. I am Husna from EC Department, Brilliant Institute of Engineering and Technology. Welcome you all to another session of our faculty development program. We are honored to introduce Dr. I. Sharat Chandra, Associate Professor, Department of ECE, Mathrusri Engineering College, Hyderabad. Sharat Chandra sir awarded with PhD degree in the field of VLSI signal processing from Geetham's University. He has an experience of 17 years in teaching undergraduate and postgraduate students. He is currently working as an associate professor in the Department of ECE and in charge for the academics and planning, Mathrusri Engineering College. He has participated and presented papers in several national and international IEEE conferences and published his research work in high-indexed scholastic international journals. He has published 16 papers in Scopus Web of Science journals. He also published 2 patents. He is a senior member of IEEE and life member of technical chapters like IETE, ISTE. He is currently the treasurer of IEEE Signal Processing Society, Hyderabad. He has previously worked as the committee member, subcommittee member, and presently the executive council member of IETE, Hyderabad. He is also the executive council member of Telangana State Committee of ISTE, chapter for the current period from 2021. He has made a remarkable impact on his students and the program. He has elicited invitation for students to participate in national exhibitions. For this contribution, he was awarded with Outstanding Educated Award for the year 2019 from International Institute of Organized Research during 4th International Convention on Interdisciplinary Research for Sustainable Development 2020. He has served as a reviewer for various international conferences and also reviewer for many reputed international journals. He has organized many workshops, FDPs, conferences with a source of funding from national and international agencies like AICTE and IEEE. Dr. I. Sharat Chandra sir will be sharing the insights on introduction to FPGA-based DSP system designs. We look forward to learn and gain valuable knowledge from his expertise. Thank you, sir. Over to you.
Sir, you are speaking on mute.
Oh, I'm sorry, sir, actually. Is it now audible?
Yes, sir. Yes, sir. It's audible. PPT also visible, sir.
Thank you, sir. First of all, I would like to thank the management of Brilliant Institute of Engineering Technology, as well as I would like to congratulate the organizers, the principal Dr. Sheikh Rustam Garu, coordinators Narai sir, Dr. Narai Garu, and Dr. Kavita Garu for giving me this opportunity to be a part of this ACT ATAL sponsored online faculty development program on emerging trends in VLSI design for signal processing and communication systems. I was asked to deliver an insightful lecture on introduction to FPGA based DSP system design, and I'll do my part. And I'll start with the basics of DSP and then why FPGAs are generally required for DSP system design. And so we'll also try to see what are the other alternatives that are present for designing DSP systems. And we will also try to talk the recent advancements based upon this DSP system design. And I'll start with some of those basics. And in order to just save the bandwidth, I would like to turn off my video. But however, if at all, if you request any of the time, I'll be happy to switch on and answer your questions. And you can stop me at any point and you can just ask me the questions. Thank you for once again. I hope I'm just turning on the PPT to the full screen actually. Hope the screen is visible. And thank you. Okay, as you all know, first of all, I hope most of the participants are faculty, those who might have already dealt some of those basic subjects related to signal processing, and you might have already have some kind of awareness what is meant by digital signal processing. Apart from that, what is appearing in the screen, I would like to just try to talk why actually a DSP is required. A DSP is a specialized area. If at all, if you consider electronics and communication engineering or the branch of electrical engineering, which actually uses DSP processors to perform some kind of mathematical operations on especially the discrete time signals. Hope everybody know this distinction between this analog and digital signals and what is the speciality of these discrete time signals. Instead of actually processing continuous or analog waves that like sound or light, generally the digital signal processors, they work with a series of numbers or sequences that actually represents the signal's magnitude or amplitude at various specific points on time. So let us simply think, let us consider an example of storing a song on a CD or a DVD. Generally, the original or the continuous sound wave, which was, let us consider it as a music signal. Originally, the form of that particular signal is a continuous sound wave, but when it is stored on a CD or a DVD, generally it was sampled thousands of times per second, and each sample was converted into a number. Actually, whenever we talk about the digital signal processing, it is always better. It's always good to remember the Nyquist-Shannon sampling theorem. It actually talks about the reconstruction. Sampling theorem actually talks about the reconstruction of the signal. And whenever we deal with the DSP is just, it is like a technology that lets us manipulating. That means something like that. The first line says that it is a process of analyzing, measuring, or manipulating discrete time signals in the form that what we generally require. Generally, all those signals which are represented as discrete times, they might be the representing the world phenomena like our sound, the music or the speech, sometimes the images, or you can also see any sensor data. Whenever you consider the applications of digital signal processing nowadays, it is spread all over, and we have the noise cancellations or the audio effects whenever we deal with this audio signal processing. And similarly, simple operations on images like image filtering, compression, that what we generally do joint pixels experts group, JPEG, or any kind of thing that what we deal with. Okay, or in the wireless communication side, where we generally deal with this modulations and demodulations of signals, and similarly error correction. Whenever you deal with any kind of any kind of application, generally DSP is everywhere, and it creates these kind of effects like noise reductions, echo, or equalizations that what we generally see. Therefore, it's a fundamental technology that is everything, whatever you consider nowadays, the applications from the smartphones or the medical imaging to radars that what we see, where we use in warfare, and seismic analysis that what we do, everything, everywhere DSP is there. And similarly, when DSP is that important, why we need to actually deal with something called as, why always we deal with an FPGA? Why only FPGAs? Why not some another other kind of devices or any other particular phenomena? Why we are using FPGAs as a preferable choice? I would like to talk on this actual important point. Previously, there were, if at all, if you see any kind of digital electronic related equipment, generally you see some boards. Most of the time, with the, you might have clear knowledge on the Moore's law. It says that for every 18 years, there will be a spike in the number of transistors that what we generally use in any particular IC. Therefore, it actually tries to talk about how rapidly the technology is changing. Similarly, whenever we talk about miniaturization of devices or making it very affordable and easier to access, generally we think about making the making this kind of circuits which are built on those kind of boards are interconnected every time, but they cannot be reprogrammed. That was the main disadvantage or the limitation that what we generally see in the olden era. So when actually given a thought about programmability, what can be done? What can be done? Then there was an era where we was talking about specialized digital signal processors for actually dealing with different kinds of DSP operations. As we all know that many of the operations in digital signal processing, they require some special kind of hardware. Let us consider the correlations or the convolutions, whatever we design, the filtering, the impulse the infinite impulse response filters or the finite impulse response filters designing, and the multi-rate sampling that what we generally do, some kind of decimation or interpolations. Everything requires a storage of large number of coefficients, which inherently actually deal with some kind of additions and multiplications at any given time. Therefore, we require some specialized kind of hardware where these DSP operations can be carried out. Therefore, there were some DSP processors actually designed where this microprocessors generally, that what we generally have doesn't seize out or will be not able to, be generally not able to do these kind of operations, mathematical operations with inherent parallelism and all. Therefore, there was a need for some different special processors which can perform this kind of operations. In that case, we could see some kind of programmable DSPs also. But however, they can be programmed, but the hardware of those kind of DSP processors can't be changed. Therefore, there comes the unique advantage of this kind of FPGAs, where you can see that the CPUs or the GPUs, the graphical processor units, they are actually sequential. They will be always doing the jobs that what we assign in the form of some kind of instructions, one instruction per second or one instruction at a time. But FPGAs offers a unique advantage where they are parallel. They perform they execute different kinds of instructions at a time, and they can perform hundreds or thousands of operations simultaneously. This is one of those, uh, this gives us the key message that FPGAs are powerful choice for DSP because of their inherent parallelism, allowing them to handle multiple computations at a time. But whenever we come across, so let us consider a CPU or a GPU, okay, in our cases. I would like to draw an analogy and try to explain this particular point. Why actually FPGA? So let us try to understand this clearly with a simple example. Let us consider a CPU. It is like a single line highway. Whenever you would like to process data very quickly, then this is something like only one car at a time. Only one car at a time. Similarly, whenever we consider a graphical processing unit, a GPU, it might be a multi-lane unit. That means it can be a multi-lane highway, which is great for once again for different kinds of parallel tasks. But the problem is here, it has a fixed structure. The road has some boundaries. It can't be changed. We can't actually have a different path whenever there is a traffic jam. Similarly, now when coming to an FPGA can be described as something like an empty field, okay, where you can build your own custom highway network and you can design your own specific circuits to perform any kind of DSP related algorithms like filters or that particular circuits which actually process data which might be flowing at a different rates. Similarly, this custom hardware, whenever you consider like an FPGA, they actually give you extreme speeds uh, and they are always predictable, and they also offer some kind of low latency. That means they can process the signals with minimum delay, which are crucial for different kinds of control systems. And these kind of advantages like um, handling large amounts of data as well as processing signals with minimum delay and reconfigurability of the hardware as well as speeding up the computational tasks, they definitely they are all going to be some key advantages which actually boost these kind of DSP computations. As you all know, until 1990s we have the ASPs, that is the analog signal processing units, uh, which were quite popular, over a some few decades actually. And with the advent of designing fast algorithms like FFTs and all, after 1990, we had a different kind of era where digital signal processing has taken over into every field of application, and we could see that uh, all over. Whenever you talk about any kind of customer application, military applications, wherever you see, you could find the DSPs. Therefore, so in order to perform different kinds of DSP computations, we require some specialized hardware. And as I said, FPGAs was a suitable choice. They are a suitable choice in order to carry out this DSP applications. Similarly, I would like to just throw a light on basic FPGA architecture. This particular slide actually explains the key components that are related to FPGA. And you can just imagine the basic FPGA architecture where you might have different kinds of blocks like input output blocks, as well as you could see the interconnections and CLBs, that is computational logic blocks and interconnections between them. They are all, this actually clearly says about the fundamental block diagram or the basic FPGA architecture, it is actually a massive grid. You can see a massive grid of possible programmable building blocks here. Okay, programmable building blocks. Generally, lookup tables. Let us consider. Oh, sorry. Let us consider the logic blocks, which are actually the fundamental units of these logic blocks. Once again, becomes the LUTs, which we generally call as lookup tables. They form the core of the FPGA, and they are the ones which are generally used for configuring, and they perform the fundamental component. They are like tiny logic gates. They are something like smaller logic gates which actually perform, which can be configured to perform any kind of logic functions, any kind of logic function that what we intend to do. And similarly, there are some kinds of flip-flops which actually stores the data. They store a single bit of data and essential for creating registers and state machines. And that is why they are enabled through sequential logic and state machines. And they are generally required for enabling or creating the registers actually. And similarly, we do have DSP slices, which we generally call them as specialized blocks. They are generally used for performing different kinds of high-speed arithmetic operations like multiplications and accumulations, the MAC units, which are ideally required for our digital signal processing operations. And similarly, there is something that what we couldn't see in the block diagram, that what I call it as BRAM, or the block RAM, that which actually is present on the chip for storing large amounts of data whenever we deal with DSP operation, generally in order to store the filter coefficients and all. Therefore, this is one of those one of those basic FPGA building block. However, there is another important thing that what we need to discuss is about the routing architecture. So these are what we generally refer to the millions of those programmable wires that which connects all those blocks that what we have talked previously. They are the millions of programmable wires that connect all these blocks together, and they allow us to create any kind of digital circuit that what we generally try to build or imagine. Okay, therefore, this is a basic FPGA architecture, and I would like to just summarize how they are different from our regular FPGA, from regular microcontrollers or the specialized DSP processors. Here I'm just considering some of those modern processors. Whenever we are trying to compare them on the present day, the most important features that whenever we try to perform or whenever we try to generally build a system, we generally look for different kinds of features. One of the 5 of those most important features are the execution speed, flexibility, power, and cost. Whenever you just try to compare here, you can see that both the microcontrollers and the DSP processors, they are one and the same. They actually work through a single core, where they perform different kinds of operations sequentially. Whereas FPGA offers the same kind of execution through parallelism, that what we call as the reconfigure, which is generally executed through a reconfigurable hardware. And speed, when comparatively, as it performs parallel operations, comparatively it provides some extremely high level of speed, where we can have some kind of customizable pipelining structures. Thereby you will have extreme speeds whenever we compare to our the present day microcontrollers or the DSP processors. Similarly, the flexibility that it offers in order to construct your own circuits in your own way, generally FPGA offers you a maximum freedom, where the hardware and software changes can be done many number of times. They can be reprogrammed, but at the cost of high powers. This is the only disadvantage. But however, when we compare to the other kind of features like execution speed, flexibility, generally we need to have some kind of compromise, and we generally try to implement through FPGAs. And now let us try to talk about the fundamental. Let us move, since until now we were talking about different kinds of basic things about the DSPs and the FPGAs. Now I would like to move to the other phase where I would like to just talk about the fundamental DSP concepts in hardware. How do we deal with them? What are the fundamental DSP concepts whenever we try to talk about different kinds of hardware? What we need to just look into. The first one is the number representations. This particular slide, whatever I would like to just, I'm trying to display, I would like to just say that what is the differentiating factors between the fixed point content or the fixed point and the floating point number systems, and why they are generally, why fixed points are generally preferred over FPGA based DSPs. That's what I would like to do with this particular slide. And whenever we consider the fixed point numbering system, they are the numbers with a fixed number of bits. For the integer part as well as the Mandisa part, generally we call it as a fractional part. And similarly, the pros related to this fixed point numbering system is that they are efficient and they require fewer logic resources and comparatively lower power when compared to the floating point numbers. But whenever we consider the other side of this particular fixed point numbers, they have a limited dynamic range and they have some kind of precision issues whenever we deal with applications like filtering and all, because of rounding off effects and all. And similarly, whenever we deal with floating point numbers, they are similar to the scientific notations with separate mandisas and exponents, and they also have wider dynamic range, and they offer some a high end of precision. When once again coming to the cons of this particular floating point number system, they are resource intensive. You need to provide different kinds of resources, and the logic that what we generally built in order to support this kind of floating point number, the hardware might be a little bit complex, and that's the only reason. Hello. Hello. Is there any kind of query or?
Yeah, sorry, sir. I
Okay.
muted that guy.
Okay. This is the only reason. Okay, since we could see some kind of hardware efficiency, the fixed point numbers are generally typically preferred of our DSPs on FPGAs. The reason is the hardware efficiency. But whenever we consider the wider dynamic ranges and high precision, the floating point number systems are the best one. But however, considering the hardware efficiency, we generally go for fixed point numbering system. Fixed point representations, as the slide actually talks, they are much simpler. They have a predefined number of bits for the integer and fractional parts, and they can only introduce some kind of quantization errors. And sometimes when compared, this hardware implementation is also much more efficient when compared to the fixed floating point numbers. Okay, this is one part that what we need to actually try to keep in our mind. And another point that what we need to always take into consideration is the data flow and the pipelining procedures. Actually, what is pipelining? Pipelining is a technique. Generally, it is used for increasing the throughput by breaking down your tasks that what is given into a series of smaller and smaller sequential stages. As the slide itself says that they are used for, it's an essential technique for increasing throughput. It breaks down all those complex operation into smaller stages with each stage running in parallel. I would like to just elaborate this particular thing where I would like to say what happens whenever there is no pipelining or without pipelining. What happens generally? Let us consider. Imagine something like an assembly line for a car. Whenever you try to take in a non-pipelined system, generally you would finish something like one car completely before starting the next one. Similarly, whenever you have a pipeline system, something like where you have multiple cars on the line simultaneously with each stage, something like your chassis or the body or the paint, something working on a different cars at the same time. Okay, I hope I'm trying to generally explain. I'm trying to talk about the manufacturing of a car. Okay, where if at all we are not actually trying to introduce this pipelining concept, that might take one car has to be completely manufactured whenever we are talking about everything, fixing different painting procedures, everything. It takes some time, but whenever we go for a pipelining stage, at any particular time, any particular car undergoes different kinds of mechanisms where it actually, and this can be applied. This can be applied here also in an FPGA. Whenever we consider, we use registers to create these kind of different stages. And this allows us to process new data on every clock cycle. As the slide, it says that each stage takes one clock cycle, but a new input can be processed every cycle. Okay. What happens as a result is you could see that you can increase the overall data rate. That means even though the total time for a single piece of data to pass through remains the same, we can see that there is a reduced latency overall and there is an increased throughput. Therefore, data flow and pipelining is generally present in this kind of FPGAs. And parallelism, and another kind of important point that this particular slide actually focuses on the unique ability of the FPGAs. It actually talks about the spatial parallelism, which is different from the parallelism in a multi-core processor. Actually, spatial parallelism is something different. It actually tries to talk about where this multiprocessor can run a few tasks at once, but however, an FPGA can implement hundreds or thousands of parallel data paths. Therefore, the spatial parallelism is something different from the regular parallel processing that what is implemented in a multi-core processor. Therefore, what is this actually? A multi-core processor, generally what it does is it can execute multiple instruction streams in parallel on different cores. You might have 2 or 3 processors or 2 or 3 different cores where they might be performing different kinds of operations, multiple operations on different cores. But whenever you are coming to an FPGA, you are not running instructions. You are actually building physical circuits. Okay, you can literally say that you can replicate a circuit like a filter. If you consider a circuit like a filter, 100 times on the same shape, you can repeat this kind of procedure. Each of these circuits actually operates independently and in parallel. Okay, that's what happens with an FPGA. This means you can process 100 different input signals simultaneously. That means that is how this FPGAs are made ideal for different kinds of applications, like whenever we generally consider for data encryption or network packet inspection. Generally, you consider different kinds of applications where there may be a requirement of many independent tasks which has to be performed at once. Okay, in all such cases, you could see that this FPGA's performance is better than that what we generally talk about different kinds of multi-core processors like specialized DSPs or something else. And similarly, another important thing that what we need to look about are DSP systems or the fundamental DSP concepts that what we need to just look in the hardware is about the filter design. Okay, so let us consider this particular FIR filter design that what I am discussing here is a conceptual introduction to a common DSP filter. Okay, let us consider a common DSP filter where, as you all know, that FIR filter simply smooths the data by averaging a series of input samples. Okay, let us consider a FIR filter which is actually related by this particular formula y of n, which is equal to sigma. Since this is finite in range, generally your k values are typically from 0 to some n minus 1 over n points. Therefore, it is related through a convolution relation. Y of n is equal to sigma k is equal to 0 to n minus 1 h of k x of n minus k. You could see here the h of k, the impulse response, the coefficients of these kind of FIR filters, these coefficients are generally very large in number, and these numbers determines the filter characteristics. Okay, so you consider different kinds of coefficients. That means you could see the same building block actually performing as a low pass filter or a high pass filter. It depends upon how the coefficients look like. Okay, these are the things which actually brings some kind of differentiation to the digital filter. Okay, therefore it is a, whenever you consider an FIR filter, it is a simple digital filter that where the outputs a particular input signal based on this kind of a weighted sum of finite number of past input samples like x of n minus k and all. Therefore, it is generally smoothing in the sense here it is something like removing the noise from the signal. Okay, therefore a simple FIR filter actually takes current input and a few previous inputs, multiplies each other, multiplies each by a specific coefficient like some particular coefficient, and adds them all once again to produce the output. Because it has no feedback loops, generally whenever we see with respect to infinite impulse responses, we doesn't find any kind of feedback loops. It is inherently generally considered to be stable, and these are very easy to implement in hardware. Okay, therefore this is another basic thing that what we need to consider whenever we are trying to build the hardware related to DSP. Okay, this is one particular area we can actually concentrate upon. And how do we generally implement it? Okay, how do this FIR filters are generally implemented on FPGA? Okay, how important it is. And this particular slide actually talks about how this FIR filters parallel structure maps perfectly onto a FPGA architecture. Okay, a parallel architecture for an FIR filter uses multiple MAC units, that is multipliers and adders. And okay, I'll just try to put in some another way. You could see the slide. You can just go through and read out of it. But I would like to elaborate it in a different way. So let us consider, as you all know, that FIR filter, it has some series of multiplications and addition adders units, and we can use this FPGA's built-in DSP slices. Okay, you can generally use as FPGA's built-in DSP slices for those performing those kind of multiplication operations, and the routing resources that what I was talking about. Okay, previously in the basic building block of FPGA, all those routing resources generally can be used to connect the outputs to a network of adders. Therefore, you can build your MAC units very easily, and whenever you tap, each tap in this filter, actually you can be its own, whenever you consider it, it can be own dedicated multiplier for it. Okay, therefore this entire structure, whenever we see with respect to an FIR filter, they can be pipelined to process some kind of new input samples on every particular clock cycle we receive, and therefore we can achieve a very high throughputs. That is what it actually says, the last point. This approach is extremely fast and efficient, allowing for a real-time filtering of high frequency signals. Okay, therefore this is how you can implement it through this FIR filter. Implementations can be done on FPGAs. Okay, so therefore in the first few slides I have actually talked about the basics of DSP, and until now I was talking about the fundamental DSP concepts. Whenever we are trying to implement on hardware, generally what are the things that we need to look over. Okay, and now I move on to different kind of thing where I would like to just describe about the design flow. The design flow, how actually high level flow chart. That means actually I would like to talk about how the data flow will be on any particular FPGA design process. Okay. Previously, you might have seen different kinds of software development, but unlike those software developments, which is something like a compiler, linker, and debugger, which actually runs those things, runs a particular cycle, FPGA design is slightly different, and it involves something like a series of synthesis and mapping steps, actually. Synthesis as well as those mapping steps that what you can see on the slide. Design entry, here we talk about something called as a design entry in the second point. Design entry is where we write our own code in an high description languages, okay, hardware description languages like Verilog or VHDL. And actually synthesis, that what synthesis is a process which actually converts or translates this HDL code into a logical circuit diagram. That logical circuit diagram, generally we call it as a netlist. Okay, therefore synthesis is a process where we generally translate this code, and then next comes the place and route step, where your logical circuit is actually mapped onto the FPGA's physical architecture, where we try to take and it is a most complex step actually, where we actually it's where the software maps the logical diagram onto the physical hardware, and then it connects all those components through those routing structures and all. What we generally also call them as interconnects. And similarly, the bitstream generation. Finally, there will be a bitstream generation that which actually creates a final configuration file that actually programs your FPGA to become your own customized circuit. Okay, this is how that bitstreaming, the bitstream generated thing will be actually dumped onto your FPGA board in order to have your FPGA board working as a custom circuit. This is what generally happens in a design flow. Whenever you would like to design a particular circuit on an FPGA, these are the steps that you need to follow. Once you start with writing your own programs in HDL languages, then try to synthesize it, and then try to configure it so that we can get the netlist, and then bitstream generation and dumping onto the FPGA board. This is what the basic FPGA design flow is. And now let us talk something more about this hardware description languages. As you all know, there are two primary HDLs, Verilog and VHDL. Unlike our high-level languages like C++ or Python, which are generally used to write sequential softwares, this high-level or hardware description languages are generally used for describing the hardware. They describe how those logic gates and the wires that what we see on the FPGAs, they are all connected. Okay. Whenever we consider HDL like VHDL, it is very something. Whenever I would like to use some words like, it is very formal, and you can see that it is morely verbose. Okay, that means we do have a lot of things that what we generally use in our academic applications, and whenever there are some mission critical applications, we generally go for VHDL. And Verilog, it is more concise. Whenever we compare with the VHDL, it is more concise, and you could see that they are widely used in all the commercial applications. They are very simple to use. Okay, whenever we compare it with VHDL, the key concept is that you need to just understand that HDL code actually describes parallel operations, as well as it also expresses some kind of concurrent behavior. That means you could see that everything not happens sequential. Okay, you could see that they are all done concurrently. Okay, there is no kind of sequential execution here, and HDL codes are generally they describe the parallel and concurrent behavior. Okay, therefore these HDLs are much more preferred. Okay, when compared to our high-level languages like that what I'm talking as C++ or Python. Okay, and these are better used for designing our FPGAs too. And coming to the simulation and verification step. Simulation, it actually, this particular slide, once again, it emphasizes the importance of how to test your hardware. Because it is very important. First of all, you need to verify your whatever you are whatever you are trying to do, whatever the design that what you are trying to do this on the hardware, before loading onto that particular FPGA or the chip. You need to actually test that hardware, and this particular slide actually talks about that importance. Simulation and verification, it is essential whenever we perform any kind of design functionality before loading it onto the FPGA. Something like whenever we try to talk about test benches, hope you all know, where we generally give different kinds of inputs for the piece of HDL code, such that we can verify the design for different kinds of inputs and check the outputs, and whether they are actually mapping the expected results or not. Okay, this is what we generally do through a test bench. And there are two different kinds of simulations styles, that what we generally call as behavioral or timing simulations. In my own way, generally I call it as timing simulation. Whenever behavioral simulation actually checks for the logic of the code, whereas the timing actually checks whether it is physically mapping or not, and is there any considerable time delay or not. Okay, this is what the basic difference between our normal simulation techniques. And then comes HLS, what I call as high-level synthesis. High-level synthesis is some other tool. It is a modern design methodology. High-level synthesis. Whenever this is completely a paradigm shift. Okay, whenever you generally consider any HDL languages or any other code, generally HLS is completely another shift. Okay, another shift where instead of writing your low-level HDL languages codes, you can write your own algorithms in high-level languages like C++ or MATLAB code, and then try to convert it into that HDL. You could see in MATLAB, okay, you can convert your .m codes directly into Verilog codes or VHDL codes. That can be done. Okay, therefore, this kind of HLS is something different than what we see, what we have talked previously, which can actually automatically translate whatever we write in high-level languages like your C or Python or C++. They can be converted into low-level codes. And what happens actually, because why I was talking about HLS is, as you all know, learning the design procedures through HDL languages is a tough task. You need to actually follow different kinds of syntaxes. Syntactically, you need to check, okay, and you need to have a lot of practical training on softwares like VHDL or Verilog in order to write at least a good code. Okay, therefore, but however, we are very much familiar with high-level languages like C or C++, and therefore it becomes very easy for us in order to write the algorithms or the flowcharts through C, whatever we are trying to map onto that particular design. That algorithms can be easily programmed through C or C++, and this particular things, they actually tries to speed up the design process for all those of us who are more comfortable with this kind of software languages. Okay, and instead of talking about hardware implementations and all, we can directly write into simple software languages. Okay, this is very easy for us, and since this particular compilers actually provides a way for debugging, it is also easier to find us and fix those bugs into high-level language, and thereby you can avoid multiple rechecking of your design and all. Therefore, this actually increases the productivity, and therefore high-level synthesis nowadays, this is the most preferable way of designing. It is considered to be a modern design methodology. Okay, and next comes, let us talk about the FPGA design boards or the development boards that are actually needed for us. Okay, I would like to talk about some high-end FPGA boards that are available for us in order to process any kind of DSP related circuit designs. Actually, the popular examples like Xilinx Zinc boards or Intel Cyclone, or you can see Altera Aria board here. Okay, they are all actually provides the necessary supporting circuitry like power supply, whatever you require, the power supply, the clocks, and the connections to peripherals like something like LEDs, switches, and high-speed connectors. They can all be available on the single board, and they are the essential link. These are some of those high-end boards which actually they provide a link between our design circuit as well as in the real world, that which actually allows us to test our own particular DSP systems with sometimes with the real-time data from the sensors that what we have, and sometimes from the cameras as the inputs, and sometimes from the audio sources, okay, or from something like a mic or something like that. They can be directly plugged onto those boards, and they can be we can directly actually have those digital inputs converted on the same boards itself. These are very high-end boards. You could see the Zinc board here, the Intel Cyclone or the Altera boards. These are all considered to be the FPGA development boards, and these particular boards support our DSP applications as well. And now I would like to talk some more advanced concepts related to our DSP. And similarly, I would also like to talk about some hardware implementation and all. Okay, and the first and the foremost, one of those my area of expertise, which I talk about, that is the Cordic algorithm. A Cordic algorithm is basically considered to be an efficient way. It is something like an efficient way. It is nowadays all the scientific calculators that what we use, they are generally built upon this kind of algorithm called as coordinate rotation digital computers. This is an efficient way of performing trigonometric calculations actually without the need of multipliers. Okay, here we doesn't require any kind of multipliers, and by use of extensive shift and add shifters and adders in order to perform different kinds of applications, we can eliminate the use of multipliers. Therefore, Cordic algorithm is one of those algorithms which actually can be used for not only for trigonometric functions. You can also use different kinds of arithmetic operations as well, and other functions like logarithmic, anti-logarithmic operations, and similarly you can use also for hyperbolic and inverse hyperbolic functions. Everything, okay, you can use this coordinate rotation digital computer algorithm in order to use for that. Okay, it's an iterative algorithm. Iterative algorithm in the sense where the steps are repeated numerous times, and they actually they are used for, as I was listing out, they can be used for calculation of wide range of functions. And the only advantage is that it eliminates that use of multiplier units, and it only uses the bit shifts and additions, which are very cheap to implement. Okay, which are very cheap to implement in any kind of FPGA hardware that what we generally consider. Okay, therefore, this makes it incredibly efficient for tasks that wherever we require some kind of real-time trigonometry operations, as I have listed some of those applications here: phase and magnitude calculations in communication systems, the motor control that what we would like to bring into a real-time systems, and sometimes related to graphics. Okay, wherever you see something like you can also talk about digital down conversion and a wireless receiver, or if you would like to calculate the phase of any particular signal, okay, then you can actually use this Cordic algorithms. Okay, this is once again a separate algorithm which actually supports our DSP applications, and they can be implemented on FPGA. Okay, this is one of those important application where you could see, and we can talk a lot more on this Cordic algorithm whenever if on any particular different platform actually. And the other application, this particular whatever you see here on that particular screen, it actually talks about the practical limitation that of our fixed point arithmetic that I was saying previously, that it is a preferred one whenever we try to deal with an FPGA. But this particular slide actually talks about that practical limitation. I was talking about the quantization errors previously. Okay, this particular slide actually discusses those practical limitations. When you actually represent a continuous signal with a finite number of bits, you could see that you will always lose some kind of data from it. That means there will be no precision at all. This actually lost data, or that precision that what we have lost, actually that accumulates to our quantization noise. I guess you all know about this. And this is a design trade-off. Okay, whenever you try to use more number of bits, that will increase precision. But what happens? You could see that there will be a consumption of more hardware resources whenever we are trying to increase the number of bits. But whenever we are decreasing it, you could see that there is some kind of noises like quantization noise, or rounding off errors, or the errors due to truncation, these kind of things. Therefore, this is always a design trade-off, whether to increase the uh, bit rate, or whether to represent them with lower number of bits. Therefore, overflow also occurs when a number actually becomes too large for its assigned bandwidth. If at all we have only a particular register which can hold only 4 bits, but your bit width is too long to hold for that particular register. Okay, that means I would like to just say a simple example here. Let us consider we are trying to add two 4-bit numbers. Hello.
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 Proceed, sir. Somebody interrupting. Proceed, sir.
Yeah. Okay. I thought somebody was asking something. That's the reason I was. Okay. Anyways.
Some interrupting only.
Okay. As I was talking here about this error correction and quantization, I would like to just take a simple example, which can be understood by everyone here. Let us consider if we are adding two 4-bit numbers. Generally, what happens is the result might exceed your 15, okay, in digits. That means you are getting an overflow there. Therefore, you require some kind of proper scaling of those particular signals throughout the design. And you might have already heard about the saturation arithmetic. This is one kind of a technique that what we generally use in order to critically manage these kind of issues related to quantization or overflow or truncation or rounding. Okay, this might have been already discussed in order to mitigate our quantization errors and all. Okay, therefore, I guess this has already come in our digital signal processing. Okay, the saturation or arithmetic is one kind of a technique which actually limits these particular issues. Okay, here, once we have this kind of advanced DSP concepts and hardware implementation issues now, I would like to talk about some applications where you can see that DSP driven systems, which when implemented on over FPGAs, how they are efficient. Let us consider a simple example or an application of audio processing. Okay, I am now trying to talk about real-time audio equalization. Okay, this particular slide actually talks about equalization concept. Okay, so let us imagine where we are trying to build a equalizer. I guess you all know about an equalizer, real-time equalizer for professional sound systems. Whenever you deal with your mics, microphones, and public address systems, you might have a equalizer system. Okay, what does that particular equalizer do? Generally, we would be using a analog to digital converter, where we will have that conversion of microphone audio signal, that whatever we receive the microphone audio signal into a digital data stream, and this digital data then fed onto an FPGA, okay, which once again contains a pipelined filter bank, where this each filter in that bank is dedicated piece of hardware that can actually process different frequency bands. Okay, therefore, this parallel nature of this FPGA actually allows all these filters to run simultaneously without any kind of latencies, or it also ensures that sound is actually processed in real time. Okay, that's what happens. Okay, and this is one particular application where you could see that audio processing is generally carried out, or the audio processing is a DSP application where it can be done through this FPGAs. FPGA can be generally used in such a way. Okay, therefore here the last line clearly illustrates about this FPGA role. Okay, it provides a low latency parallel processing needed for real-time audio. How I have just explained it. Okay, FPGA have different kinds of filter banks, and the digital data, whenever we are feeding it to this FPGA, which actually contains numerous filter banks, they try to each filter in that filter bank actually performs a different piece of work on the hardware, and that can actually process different various frequencies that are present in that particular same signal. Okay, this is one such particular case study. You can actually observe it. Okay, by feeding your FPGA ports through a simple music signal or a speech data, you can actually see what happens there. How does this FPGA clearly understands and tries to differentiate between different frequency bands and all. Okay, therefore, after processing, once again, this processed signal is then sent to back to your digital to analog converter, and then once again it is played through speakers. Okay, this is what happens in a public address system, and where this real-time audio equalization is done on FPGA. This is one such application, and I would like to talk about another application where you could see this DSP related application which is implemented through FPGA. Let us explore or consider a simple 5G base station, okay, where we generally carry out this baseband processing and all. You know about this wireless communication, which actually requires encrypted, okay, that means which actually requires some kind of fast and complex signal processing. Okay, whenever we are performing wireless communication, it is one of those applications where we require faster processing, and it also performs a processing between different kinds of complex signals. Okay, what is the role of this base station? Actually, it is required. It actually need to handle those multiple channels and process data from hundreds of users simultaneously. Okay, that base station will does that particular job. And now, whenever you consider an FPGA, it performs this kind of critical tasks such as baseband processing. It is carried out. Similarly, the channel coding can be done, and the modulation and demodulation operations can be done. This all can be done through a single FPGA. Okay, therefore, its ability to actually process this kind of massive amounts of data in parallel. Okay, so once again, in parallel at low latency. Okay, with the low latency, actually it makes the ideal platform for these particular systems. Okay, so that means I would like to I'm trying to just explain different kinds of applications, how the DSP applications are implemented through FPGAs. Okay, these are two such applications which are classical examples that we generally try to see in our day-to-day use. Okay, I hope that it is somewhat relatable. Okay, and I would like to now talk and now shift once again my focus onto another particular thing, because we have very time limitation of just a 1 hour or 1.5 hours. I can't actually try to say the real-time DSP implementation through FPGA. I can actually handle a one-day session for you on this particular real-time DSP implementation. But however, now I would like to talk about one of those present-day IP core systems. Okay, IP cores or design reuse concepts. Okay, I would like to just explain you and give you an idea about this IP cores. What are actually IP cores? Okay, they are simply saying they are pre-designed reusable hardware blocks. Okay, so we were talking previously about the FPGA, where we can actually try to configure the logic blocks, okay, then and there upon, for our use. But IP cores are something different. IP cores are pre-designed, okay. In order to perform a suitable application like a convolution or a FIR filtering, we have a predefined IP core, okay, intellectual property core, which can be used for that specific application, and therefore you can optimize your circuit blocks and all. Okay, as it says that, okay, it is also a tested block. Okay, it is not only a pre-designed or optimized block, it is also a pre-tested circuit for performing some specific functions like let us consider an FFT, or whenever we would like to see that a specific application like an Ethernet controller or high-speed memory interfacing or anything like that. Generally, you have a specific IP core for it. Okay, therefore, instead of designing this kind of complex blocks from scratch, you can have your license and you can integrate them onto your particular design, which can actually reduce our developing time, or that means development time and risk also. And many of the times, whether you're not sure about your design, whether until the last step of your design, whether the design will be matching the expected results or not. These kind of things can be minimized through IP cores. IP cores simply are pre-designed reusable hardware blocks. Okay, please remember these things. And there are many types of IP cores which can be available for DSP applications. Okay, so one such particular application or one such particular examples were some of those examples were already listed here. But however, there are two major vendors which are actually providing extensive IP cores for us. Okay, the Xilinx IP catalog and the Intel IP library. They both have different kinds of IP cores, which actually gives us some predefined logical blocks for us, which can be used for performing different kinds of operations related to DSP, like FFTs. A pre-optimized block for performing FFT is already available. You need not write once again a program, okay, for performing FFT of some so and so particular point or something like that. Okay, for these are all the examples that what I was discussing on this particular slide are all the basic DSP operations like FIR compilation, okay, or the FFTs or DSP function cores like multipliers or adders, MAC units, and other arithmetic units. Okay, these are all some simple DSP blocks which are available in the form of an IP core. Okay, they can be just borrowed from this Xilinx IP core, IP catalog, or the Intel IP library, and they can be used on your FPGA, where you can actually pretty much sure about your design, and you can also bring your design costs and all down. Okay, therefore this is one such particular okay, I would like to generally say how to use our IP cores in our designs. Okay, how to use them. So let us consider the design flow. As I have already discussed different types of IP cores available for us. Now I would like to discuss about what are all those design. Okay, I would like to just discuss about explain you about the simple process. Okay, how to integrate your IP core onto your design. Okay, let us come up. I guess you might have used a GUI, what we call as graphical user interface. You might have designed something in your MATLAB or any particular project implementations. You might have a interactive user interface generally. Okay, that graphical user interface generally what we generally do is in your Xilinx IP catalog or your Intel vendor, that whatever vendor library, whatever you have, generally there will be a GUI from where you can actually select your desired IP core, and then it is just like what you see in your SPICE simulation software, where you can just pick up some of those transistor or any particular circuit or a component, and you can just try to connect them through wires. This can also be done through IP cores. You can just try to select your desired IP core. You can configure through your parameters that whatever you require, and then the tool generates the HDL code for your IP core. You then just instantiate it and connect this IP core to your own design in your HDL file. This is what happens. This is a modular approach, which actually simplifies your development, and it also makes your design pretty much easier to actually debug for errors and maintain it without some error prone. Okay, this is what a design flow of an IP core is. Okay, it is as simple as that what we generally do in our multi-sim or PSpice softwares. Okay, where we generally pick up and place it and just try to connect it. Okay, this can be done in your through IP cores as well. Okay, and coming to the another kind of FPGAs that are generally available, what we generally call them as design for reusability. Just as in software, writing reusable hardware code is also crucial. Okay, therefore this IP core design is something like that. Okay, the best practices that what we can do is using modular and hierarchical designs, using generic parameters to make modules configurable, and keep your interfaces very simple and well documented whenever we are trying to actually check the particular specifications of any particular IP core or something like that. Yeah, documentation should help us. Okay, that what is actually expected from the design for reusability. Okay, and then comes something called as system on chip FPGAs. System on chip FPGAs. These are something like they combine the functionality of both your hardcore processors like ARM, Cortex-A, and then with a programmable FPGA fabric. Okay, let us consider something like on a single chip. Okay, this particular SoC FPGAs help us to actually try to combine both these flavors of hardcore processors as well as with this programmable logic. What is the benefit of it? SoC FPGAs like I have shown you the examples like Xilinx Zinc board that what has been shown previously. It offers the best of both the worlds. Okay, that means it offers a SoC board. It is, whenever you consider it as a system on chip, it is the best one that we can look at. And similarly, whenever you look for an FPGA board, then also it becomes the same. Okay, therefore, these processors actually they runs through operating systems. They handle complex control logics and then manages networking also. Okay, therefore, this particular FPGA that is available here that will act as a high-speed accelerator for your DSP related tasks and all. And whenever these two processors are integrated, that means whenever we are trying to combine both of them are tightly integrated with a very high speed bus generally, then you could see that they will be trying to communicate between them and with extremely low latency. Okay, whenever we compare the latency here, that will be very small. Okay, therefore there will be high speed communication between that particular processor and FPGA. Okay, this is possible through SoC FPGAs. And similarly, another point that what we can talk about is our on-chip debugging tools. Okay, whatever we talk about the JTAGs, the standard interface for your programming and debugging. Okay, this actually talks about use of those on-chip logic analyzers. Okay, I was talking about different kinds of units like JTAGs, integrated logic analyzers, which are embedded within the FPGA that allows you to actually check and various types of signals which are in real time. And if you consider a Xilinx integrated logic analyzer or Intel's signal tap is one another unit which is called as an on-chip debugging tool. They are all essential for debugging a design which actually run on your actual FPGA. They are like something like your digital oscilloscopes, which are actually built directly onto your chips. Okay, therefore, this particular on-chip debugging tools help us to select internal signals within our design, and then they try to stream their values back to the development environment, and they'll allow us to see what's happening inside. Okay, therefore, what we can actually know what is happening inside that particular circuit in real time. This can be done through our on-chip debugging tools. Okay, therefore, having an FPGA really helps us in order to understand the circuits better. Okay, and how does this debugging flow happen generally? Okay, whenever you would like to, this particular 5-line explains you the step-by-step process. How does a logic analyzer actually work? Okay, the first one is we will be identifying the signals that what we would like to monitor, and then instantiate an logic analyzer core in our particular design, and then the tool synthesizers are designed with that particular ILA. ILA is nothing but that logic analyzer, and then once a design is on the chip, then we connect it on the connect to that FPGA via a JTAG cable, and trigger that particular logic analyzer to capture the data. Okay, this is what happens actually, and then the data is sent back to our particular computer, and then you can view all the waveforms in your debugging tools, and then analyze the timing, and something like you can value your signals and everything that can be done on that particular computer. This is how this debugging flow happens with the availability of an FPGA. Okay, and I would like to once again revisit the test benches that what I was talking previously. Test bench is once again how important. I would like to stress upon here how important a test bench is. Okay, you can consider it as a software equivalent of your test bed of your hardware. Okay, that means whenever you would like to test your hardware, this is a software equivalent, the test bench. Okay, it generates different kinds of it becomes a key part of our verification process, and whenever you are writing a very good test bench, it will not only provide the inputs but also helps us to check the outputs against those particular expected values, automatically throwing out different kinds of errors. Okay, different kinds of errors for us. Okay, therefore writing a good test bench, a thorough test bench, is often more time consuming than actually writing the design itself. Therefore, it should be it has to be a important step for creating a robust as well as whenever you are trying to build a reliable system, it is very important that you design a very good test bench. Okay, that helps us to make our design very pretty much efficient. Okay, and coming to this formal verification, generally, how does we verify whatever we write onto the FPGA? How does we do that? Okay. This is once again an alternative to our simulation that what we have talked previously. Actually, your simulation can prove that the design can actually work for a specific set of inputs, but it can't verify, it cannot prove that it works for all possible inputs. Okay, that means your test benches or the simulations actually works for only the given inputs. Okay, but it can't assess what are all those possible inputs are. But your formal verification can help us use different kinds of mathematical methods to prove the correctness of the design. Okay, whether your design is correct or not without any particular simulation, your formal verification helps us. Therefore, it can prove that, for example, let us consider a circuit. Actually, if there is some kind of an undesirable state, and it should not enter into that particular state. It is something like computationally intensive, as I was actually trying to say here. Whenever it is crucial for us to build that particular critical components in the systems where failure is not at all an option. Okay, therefore, in such case, we generally go for this formal verification and all. And whenever we try to deal with FPGAs for different kinds of DSP applications, there are some common mistakes that every designer does. Okay, I would like to bring to your notice about the common pitfalls that what a general common error that what we generally do. Okay, the most common error is the timing violations. That means this is a most frequent issue. Whenever we consider it occurs whenever signal doesn't settle to a stable value. Okay, it doesn't arrive in time in the sense it doesn't settle to a stable value before the next clock edge, leading to that particular unpredictable behavior. Okay, this is what I am trying to put in as doesn't arrive in time means. Okay, and similarly, the next one is the resource overflow. That means if at all our design is very complex, then it might not fit onto the chosen FPGA chip. In such case, it requires redesign. Okay, therefore, you need to be more resource efficient whenever you are trying to plan for implementing any particular design on FPGA. Therefore, resource overflow shouldn't happen. And another one is reset issue. That means here I would like to talk about this clock domain crossing and all. A very difficult and dangerous problem. This is one of those particular dangerous problem wherever it occurs whenever there are some signals which move between two parts of the design operating on different clock cycles. In such case, what can happen is there might be a case where we can lose our data, and this will actually create some kind of meta stability in our particular design. Okay, therefore, this kind of reset issues and clock domain crossing, this has to be avoided. Okay, the timing of violations and resource overflow, this should be this should be avoided in order to have a very good design that can be clearly demonstrated by implementing on an FPGA. Okay, therefore, these are some of those things that what we can actually trying to keep in our mind whenever we are designing. And there are some another future trends, the future of this FPGA based DSPs. Okay, nowadays we are more hearing about this edge AI, artificial intelligence, where FPGAs are being used for accelerating machine learning inferences on devices at the edge. Okay, that means they are their low power consumption and high parallelism actually makes them ideal for accelerating this kind of machine learning inferences. Okay, it doesn't have any access to the cloud. Edge devices generally have access to the clouds, but here it doesn't have any access to the cloud. And there comes something like IoTs, where FPGAs enable real-time sensor fusions and control in smart devices. It can be done. And similarly, high-performance computing. FPGAs are being generally deployed in data centers, like reconfigurable accelerators for computationally intensive tasks, like database queries, genomics, financial related modeling and all. Okay, therefore they are generally used for these kind of high performance computing applications. And in such cases also FPGAs are generally used. And this is how DSP systems can be implemented over FPGAs. Okay, this is how I'm expecting the future of. It is happening today, but however, in future we can still see more, since we are now data hungry. Therefore, data centers actually require this kind of designs. Okay, and another such kind of future trend is this adaptive computing. Okay, we try to understand this adaptive computing and the role of FPGAs through a small slide here. It is the idea that the adaptive computing is something like an idea which actually says that whenever you have a hardware, it can dynamically reconfigure itself in order to meet those particular changing working demands. Okay, whatever you would like to change. That means you are giving multiple instructions in different kinds of times. Okay, in a very small times you are trying to change what your system should do. In such cases, this adaptive computing role comes into play, and this FPGAs are now trying to actually have this kind of inherency about this adaptive computing techniques and all, and they are actually trying to use this concept of adaptive computing. Therefore, unlike a fixed application specific integrated circuits, your FPGAs can also be now used, can be reprogrammed to act as a video encoder 1 minute, and then in the next minute they can be used as a networking controller, and in some another minute for different kinds of applications and all. That is how our future-proof systems are actually built. They are going to be very much flexible, and they are going to be very much efficient, and they can perform different kinds of applications in different time intervals. Okay, therefore this can be done through adaptive computing. Okay, this is one such particular design. Therefore, now I have almost come to the end of my brief lecture on this FPGA introduction to for the application of DSP related systems and all. I would like to just summarize what are the things that I have discussed for the last 1 hour or so. That is, one thing is about the FPGAs. They are uniquely suited for DSPs because of their parallelism. The first and foremost concept that what we need to look into is the parallelism. And then the design flow involves writing HDLs, simulation and synthesis. And pipelining and fixed point arithmetics are key hardware design techniques. And I have discussed something like IP cores and high-level synthesis codes like MATLAB, where we can convert the C into a Verilog or something like that. They can actually significantly simplify the design process and all. Okay, I have touched these kind of things, and I hope that this might have actually given you an idea how these FPGAs are used for the implementation of our DSP related system designs. Thank you all. If you have, I'm open for different kinds of questions for the next 5 minutes or so. Hello. Is anybody here?
Yeah.
Am I still connected? Yeah. Okay.
Yeah. Good evening, sir. Actually, your lecturing is very nice, but I have a small doubt, sir.
Yes, sir.
Sir,
Yes,
whether we can
sir,
able
one
to
second, sir. Can I switch on my video? Okay. Yeah.
whether I can able to analyze the transient analysis in our FPGA, sir? How we can able to do this transient analysis? Is it possible?
Transient analysis is something closely related to the timing constraints, sir.
Yeah,
I
yes,
guess
yes.
you are
Because
talking about the
because
static
we are
and dynamic timings and all. Yes, yes.
Because we are using different digital components for accessing our applications, so we
Yes,
will
sir, yes.
face so many transient to pass the data from one device to the other device. Is there any provision to calculate that analysis?
Yes, sir. Yes, sir. There is a provision.
If it possible, now you can give the suggestion how we will do it, sir.
Yes, sir. Yes, sir. As I was talking about different kinds of boards that are available right now, something related to the Zinc boards and all, we do have different kinds of simulation software that actually help us to check for the different kinds of results related to this timing constraints as well as the power. We do have different kinds of GUIs which actually help us to analyze different parts of your designs. They can all be done in all the present day related boards.
And also now I am working
Yes,
ANN on FPGA, artificial neural network on FPGA.
yes, sir. Yes, sir.
So just now only I started my work,
Yeah.
but previously I have done my research in FPGA only, but I not
Yeah.
included this concept. So now I try to import this ANN on FPGA. Is there any idea about this, sir?
Yes, sir. I was actually trying to talk in my previous slide where I was talking about the future trends. Okay, I was talking about the Edge AI. FPGAs are now becoming a key component for your artificial intelligence related concepts.
Yeah, yes, sir.
Yes, sir. And therefore, this particular lower power consumption of FPGAs as well as this high parallelism, actually they make more ideal for this kind of applications, sir. They are actually nowadays FPGAs are being very much accelerated for machine learning interfaces on this kind of devices, and they don't have any access to the cloud. That is the only problem. Okay, I was talking about edge computing, but they doesn't have access to the cloud. But anyways, nowadays they are all equipped with this kind of handling machine learning related interfaces and all. They can be done, sir. They can be done. Sir, I think you are muted, sir. You are muted.
Normally we are using Spartan 3 or Vertex, sir. Suppose
yes,
you
sir,
are going to inbuilt ANN, this FPGA will support? No.
No, sir. No, sir. They are somewhat older generation FPGA boards. so you try with the new series of zinc boards or so, they are definitely helpful for implementing this kind of ANN related applications as well.
Okay, okay. Thank you, sir. Thank you.
Hope I have given you some perspective related to this FPGA implementation of DSP based system designs. And I'm very much interested in this. There are some procedures where I guess that most of you might have a subject called as VLSI digital signal processing systems. The other parts of South India, generally in the universities related to Tamil Nadu, this becomes a regular subject. But however, in Telangana and all, we wouldn't see this subject here more interestingly. But there is a textbook which actually talks about the VLSI implementation of DSP systems, design as well as implementations. Keship K. Parhi. Actually, it gives you more basics related to this particular course, as well as this humor based. That particular textbook also is very much helpful for understanding this particular concepts. Hello.
Hello.
Yes, sir.
Am I audible?
Yes, sir. Yes, sir. Arshad Kumar.
Sir,
Yes, sir.
we can. So, sir, can you suggest any open source tool for the verification purpose? It was which is effective.
As I was
Actually, I know
talking.
about something in partners.
Yes, sir. Yes, sir. Anything that means at what level you are trying to ask about the
For
verification?
Verilog and system Verilog. Actually, I have started my PhD on the risk-based 5 verification. Okay?
Sir,
So
yes, sir. I have clearly understood. Generally, in order to implement your Verilog related programs and all, you require a licensed tool. Yes, 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 sir. Yes, sir. I guess that you doesn't have any kind of open source tools. I was talking about that HLS, okay, high level synthesis, where MATLAB codes can be converted into your Verilog. That is one way of checking your. That is one way, but I'm not actually trying to talk about the original HDL synthesis and all. But I come across something called as EDA playground on internet, which can be implemented on. Yes, which can be used. You can use different kinds of tools, sir, related to Synopsys or Mentor Graphics or any other tools can be implemented, where you can write your small piece of code of your Verilog, and you can just try with different simulators, and you can just check with that. Okay, that might be helpful for you as of now, if at all, if your codes are
some
like
tools I
small.
know about that. Okay, some online browser are available for virtual lab. Okay,
yes,
but I need an open source tool for that. If is it available or not? If yes, then please
yes,
suggest
sir.
me.
Yes, sir. Yes, sir. As you have pointed out this, if you might have seen different kinds of outputs related to this timing constraints or power delay outputs or anything.
Right.
Generally, it comes out to be a because of the CMOS related issues and all, which are handled on different platforms in a different way. Generally, you get different kinds of results on different simulation tools. Therefore, it is always better to use, if at all, if your application or if your use is only for academic purpose, then only prefer different kinds of open source, or you try to prefer different tools that are available freely. But it is always preferred. It is always preferred, if at all, if you are trying to build a particular IP core or you are trying to bring out a chip, then it is far more preferred only over a industry grade tools. Which is
for the commercial purpose, you have to purchase the license.
Yes.
Academic purpose or research purpose.
For academic purpose, I guess that some of them, they are actually providing some licenses on YouTube. If at all, you can listen to some of those lecturers. They are actually providing some links where you can download your multi-SIM or kind of softwares freely. You can do that,
right.
sir. Yeah.
Okay, bro.
That is the only way I found actually
No,
having our
no,
yes.
Thank you, sir.
Thank you, sir. Thank you.
So it was very nice lecture.
Thank you, sir.
Thanks.
Thank you. Is there anything else that?
Sir, if it possible, you can share your PPT, sir.
Definitely, sir. Definitely. I'll
Okay,
share the PPT with you.
Oh, because for the further implementation, we can access your PPT.
Yes. Sir. I'll share with the organizers. They will in turn share with you.
Already I post the message to them.
Okay, sir.
Thank you, sir.
If there is nothing much, then we shall end this. As the time is 9 o'clock, I hope that many of you might be waiting for your dinner.
Thank you, sir.
Thank you, ma'am.
So much for your enlightening lecture on introduction to FPGA-based DSP system design. Really, your expertise has certainly enriched our understanding of what is from the basics DSP, filters on fire filters on FPGAs, design flow, codic algorithm, SOC FPGAs, and all, sir.
Yeah.
So before we conclude, is there anyone with final question? So I would like to thank you again, sir, for your contribution to our faculty development program. I hope the insights gained today will inspire new approaches in our teaching and also in research too. Let's end the session with a vote of thanks to our esteemed resource person, Dr. I. Sharat Chandra, sir. Thank you, sir, and thank you to all the participants. Thank you.
Yes, I do thank all the participants and all the organizers for giving me this opportunity. Thank you all. Have a nice day.
Thank you, ma'am.